Welcome back. Last time we talked about inscribed angles. Those were angles that had their vertex on the circle. And today what we're going to talk about is when two objects intersect and their vertex is not on the circle or at the center, in the case of a central angle. And we're going to look at, in this video, when two secants intersect. And when two secants intersect, that intersection can happen either inside the circle or outside the circle. So we're going to examine the first version first. That makes sense. We're going to see what happens when two secants intersect inside the circle. Sometimes you'll hear people refer to this as two chords intersecting, because since the intersection happens inside the circle, we could consider chord AB and chord CD in their intersection at point P, which isn't necessarily the center of the circle. And we could say that that's two chords intersecting because all the action happens inside the circle. But I like to think about this as two secants intersecting because chords are just parts of secants. So let's take a look at this. And I've colored in some things here for our help. We're going to be examining angle DPB the whole time. And what I've done is I've colored in the arc that it's facing, arc DB, and I've colored in the arc that's away from angle DPB, or maybe you like to think about it as the arc that the vertical angle is facing, arc AC. And I've colored that one in red. And we might be able to have a conjecture about the relationship of angle DPB to the arc measures that I've highlighted here. Do you have a conjecture? Let's see if your conjecture holds up when we change the size of these arcs. So let's make this 40 now. Does your conjecture still hold up if this arc measure here is 40 and this arc measure stays at 60? Do you still get that angle DPB follows in your conjecture? Let's see if your conjecture matches this conjecture. That angle DPB appears to be 1/2 of the sum of those two arcs, aka 1/2 of the average of the arcs. And that is the theorem that you are going to try to prove. You're going to try to prove this conjecture to be true, that if I take the average of the two arcs, that will equal angle P if that intersection happens to be inside the circle. As a way of helping you, giving you a little hint on this proof, one way to approach this proof is to draw in an extra chord here, chord AD. And by drawing in chord AD, we've actually created two inscribed angles. Can you see them? Can you see the two inscribed angles that we found? If you can see those two inscribed angles, can you find the value of those inscribed angles? And once you find the value of those inscribed angles, how do those angles relate to angle DPB? You might have to go a long way back to our study of triangles to come up with a theorem that handles this situation. And once you've done it for some values like 40 and 60 and gotten 50, try it with some other values. For example, you can try other numbers in there, or if you want to try some variables, like put in a 2x for this angle, or this arc measure, and a 2y for angle AC, and see if you get that angle DPB is 1/2 of 2x plus 2y. In other words, if it's just x plus y. So that is what happens when we have the intersection inside the circle. Let's take a look at what happens when the intersection is outside the circle. Maybe the same conjecture holds here. And let's go to 30 degrees maybe for arc AC. And when we get to 30 degrees for arc AC, 60 and 30, nope, 15 isn't the average. So the same conjecture doesn't hold, unfortunately, for this intersection point P being outside the circle. Well, let's see if we can come up with another equation, though, that handles it. We only have one data point here, 60 and 30. Let's make another and see what happens. Maybe 60 and 40. So 60 and 40, we end up with 10 degrees here for angle P. Whereas when it was 30 degrees, we ended up with 15. See if you can come up with a conjecture that relates the far arc here, BD, to the near arc, AC, all the way to this angle P right there. Was this your conjecture? That 1/2 of arc BD minus arc AC equals angle P? That is the conjecture that we're going to try to prove. And again, you'll notice I use that terminology, far and near. It's really useful to think about it that way, that we're doing 1/2 of the far arc minus the near arc. That's what we're going to try to prove. And again, to help us, to aid us in that proof, what we're going to do is we're going to draw in arc AD here. And when we draw in arc AD, we've again created some inscribed angles. One here at angle A. Can you figure out what that angle is? One here at angle D. Can you figure out what that angle is? And once you have those angles, how can that help you find angle P and see that it is always going to be 1/2 of far minus near? Again, after you've tried it with some numbers for D, B, and AC, try it with some variables and see if you get this same formula. All right, we'll see you next time when we will discuss other objects intersecting and circles. See you then.